Hi everyone, and welcome to our first session on synchronous machines. By the end of this session, you should be able to describe the construction and theory of operation of a synchronous machine. This is much simpler than that of an induction machine, so it shouldn't take us too long. Now, synchronous machines are called synchronous because they run at the synchronous speed. There is no slip as in the induction motor, so whatever is the frequency you give it, that is the speed that it will come out running at. And about 95% of all generation worldwide is done using synchronous machines, whether it is from hydro, from coal, or from natural gas, as we have in Trinidad and Tobago, or diesel up in the some of the other islands, or geothermal. They all eventually make their way to a synchronous machine, turning the turbine of a synchronous machine so that you could produce three-phase power. Now that is changing a little bit because we have wind turbines using doubly fed induction motors and solar panels producing DC. But for the most part, it's still synchronous generation. And the frequency, as I said before, is simply governed by the speed of the rotor. So if you need to change the frequency, you simply adjust the speed. So to give you an overview of the motor, we have the three windings of the stator, winding A to A prime, B to B prime, C to C prime, and we have a magnetic flux direction associated with each one of them. Now, for the purpose of generation, we energize these windings, and when we energize these windings, we create an electromagnet, and as the electromagnet spins, then it cuts the conductors and it induces an EMF in each one. And if we look at the three of them together, we will see that these are the three-phase powers. So the three-phase voltages that we get, they're all shifted by 120 degrees apart because the magnet cuts them 120 degrees. They're separated through 120 degrees. So the North Pole will pass here 120 degrees after it passes the next one or the previous one. So in the large generators, I just saw this reminder come up, for the large generators, the DC, and I'll show you some pictures of this after, to get this DC current here, this is on the rotor, you actually mount the exciter, which is a little DC generator. You actually mount that on the shaft of the machine. So this synchronous generator is so large that you actually have another motor mounted on it, and you'll see here, this is the synchronous generator, right, called an alternator, 500 megawatts, 12 kV, 60 hertz. So this is a lot bigger than the ones we have in Trinidad, and I think the maximum we get to is just over 100 megawatts. So this is a 500 watt generator, and to get the DC, you see we connect here through these slip rings. These are not split rings, they are slip rings, because we have a DC generator here that is mounted on the shaft, and it is producing DC power. And to connect that DC power or from the shaft to this rotating system here, the magnets being the electromagnetic on the rotor that is spinning, we have to connect it through a slip ring. So this is the basic outline of the synchronous generator. And just to give you an idea of how big this is, if you look here, you'll see that there's a scaffolding built on the inside of the stator. So this right around the outside here is the stator of the machine, and it is so big that you actually have a scaffold inside it, and you could see there are people here standing on the edge of the machine. So these things, and I think that's one person down there as well. So these things are pretty huge machines. And this is another picture showing a rotor coil with a 4-pole DC winding. So just to give you some idea of how big these are, you have, this one is 230 megawatts, and you have someone standing on the inside of it, and you could get them from that all the way down to 5 kilowatts, which are the little sort of machines we might have in the lab. Now, regardless of what size you're looking at, each one of them would have a stator and a rotor, as all our other machines have. And the stator is set up exactly the same as in the induction machine. 3-phase sinusoidally distributed windings. They can be connected in Y or delta, and if you energize them, you get the same constant rotating magnetic flux as in an induction machine. So if you want to understand the flux distribution set up by a synchronous machine, it is exactly the same as the induction machine for the stator. The rotor, now there are two main configurations. We have what we call a cylindrical rotor, where you basically have a cylinder of soft iron and you place the conductors within it. And then the other one is what we call a salient pole. Salient simply means sticking out, and you could get here more than 2 poles, and you'll see north south alternating, just like we did with the induction machine. So and this has its independent excitation. So unlike the induction machine that relied on generating a magnetic vector rotating, and that rotating magnetic vector cut the field of the rotor, which then induced a current and gave rise to the creation of its own magnetic vector. Unlike that, here the stator and the rotor are independently powered, and the rotor could be a permanent magnet or an electromagnet, but they're independent, so they each have their own magnetic field associated with them. And just to give you an idea what this might look like, here you see the salient pole sticking out, and here is another one, so you get some idea of what the size of these things are. This is another salient pole rotor here. You see the poles there, and a cylindrical rotor, as you could see here. So the cylindrical rotor, again, we place the conductors within the body of the cylinder, and the salient pole, we simply wrap it, and the wrapping direction of the windings have to produce poles of alternating polarity going around the coil. Remember, this north-south will be determined by the direction in which the current travels here. So when the current travels in this direction, it will create a north pole, and then you have to wind it around here so that you get a south pole on this side. So that is what you have to do in order to get the salient pole to work the way you want it to. So just to go back through the basics of operation, for the generator, you energize the rotor. This is the rotor here with your north and south pole. You energize the rotor with a DC source, and then you must provide some mechanical energy to this. So that could be in the form of steam, which could come from burning natural gas, or could come from the heat from your geothermal plant or your nuclear plant, or any of those things. It could come from a hydro turbine. You have to provide some sort of mechanical energy that will turn this magnet, and when the magnetic field cuts the conductors, you generate an EMF. On the other hand, when we have a motor, then we have the rotor energized still, but it is not, no mechanical input is being provided to it. We provide the voltage, the 3-phase alternating voltage on the stator side. That sets up our magnetic vector, and that magnetic vector interacts with the rotor field and pulls the rotor along, and that is what gives us the motor action. So that is the basics of the synchronous machine. you'll see that it is not very difficult to understand the operation. It is basically a rotating magnet for the generator, and similarly, for the motor, you have a stationary magnet and you create a rotating magnetic field, and that pulls the magnet along. The magnet keeps trying to align with it, and it does that at the speed of the magnetic field created from the stator. So this is just the basic operation, and that is all that there really is to it for this level for the synchronous machine. So by now you should be able to describe the construction and theory of operation of the machine. So you should be able to talk about the construction of the stator, which is the same as we did for the induction machine, the construction of the rotor, which you could have the cylindrical rotor or the salient pole rotor, and you should be able to describe, if it is in motoring action, the fact that you have the rotating magnetic vector set up by the stator which pulls along the rotor, or if it is in generating action, you have the rotor field set up and you mechanically turn it, and that creates the EMF, that generates the EMF in the stator windings. So next time we will look at the actual equivalent circuit, how it is developed, and what are the things we could do with it, because it gets very interesting. We could do a lot of things with power factor and so on using the synchronous machine. So we will look at the phasor diagrams, and we will look at how the equivalent circuit is developed in the next session.